Welcome to Ganita Samayaha, an interactive learning space. Children, as I proceed with the teaching, please answer to questions whenever it is posed. This will help you in the learning process. Also, please don't forget to have the writing materials with you whenever you watch this video. And after you watch, please subscribe, like and share the videos. Today's class we will start learning about real numbers. This is real number part 1. Okay. Then what are real numbers, children? What do we mean by real numbers? Yes, numbers that are real are called as real numbers. Fine. In what sense are they real? Yes, they must exist. And exist means what again? We must be able to locate them on a number line. So the numbers that exist and can be located on a number line are all real numbers. Let us quickly go through what real numbers mean and understand them in a detailed manner. Here I have got a number line and I have indicated the origin as well, children. Now I want to locate a few points, say 1, 2, 5, 10, etc. I'm sure we will all be able to locate all these numbers on the number line. That means all these numbers exist and they all have a place on the number line, and that place is unique. In the sense, no two numbers can have the same place on the number line. Okay, children. And so what are these numbers from 1 to etc. up to infinity called as? Yes, they're all called as natural numbers, and all natural numbers have a place on the number line. That means all these numbers exist and so they are all real. Is it clear, children? Okay. Now what if I add 0 to this group? We know 0 is also has a place on the number line. So it also exists. Now this entire group from 0 onwards to infinity is known as whole numbers. So all whole numbers are real numbers. They all exist and have a place on the number line. Is this clear, children? Okay. Further moving on, suppose I want to locate a few negative numbers. Say for example -3, -8, -11. Okay. We know that it is possible for us to locate all the negative numbers, the infinite of them on a number line, and they all have a unique place on the number line. That means all these numbers also exist. They are all real. Okay. And what is the set of these positive numbers, negative numbers along with 0 known as? Integers. So all these integers are all real. They exist. They have a place on the number line. Is that all, or do we have more numbers? Let us see, children. Yes. What about these numbers like 11 by 2? 11 by 2 means 5.5. It has a place on the number line. 8.795 up to 3 decimal place. And here minus 4.0346. Yes, all of these numbers have a place on the number line. Last year we have tried to locate such decimal numbers on the number line, isn't it, children? Yes. So just not this one decimal place or 2 or 3 decimal places. Even if you have infinite decimal places, you will be able to place them on the number line. That means all these numbers exist. They are all real. And what are such numbers? These decimal numbers known as? They are all known as rational numbers. And what do we mean by rational numbers? Numbers that can be expressed of the form P by Q. Numbers that can be expressed of the form P by Q, where Q not equal to 0, P and Q are integers. Such numbers are all called as rational numbers. So the examples that we have taken here are all rational numbers. They all can be expressed in the form P by Q. Okay. Fine. I have got a few more number here. Minus root 5 and plus root 2. They two have a place on the number line. Last year we have tried to locate root 2, root 5, root 3, root 7, etc. on the number line. Not just these numbers, there are many more numbers and all of them have a place on the number line, which means they exist. They are all real. And such numbers, they are all called by a name. What is it? They are all known as irrational numbers. What are irrational? Simply not rational. That's all. Okay, children? All rational numbers can be expressed in the form P by Q, I told you. So, is 5 a rational number? Yes, since it can be written as 5 by 1. 5 and 1 are integers, isn't it? So it's a rational number. Root 5 is not a rational number. It is an irrational number because it cannot be expressed of the form P by Q, and the decimal expansion of these numbers will not terminate and it will not repeat. Such numbers are called as irrational numbers. I can hear someone saying root 2 can be written as root 2 by 1. Fine. It can be written as root 2 by 1, no doubt. But what is the other condition? They must be integers. P and Q must be integers. Root 2 is not an integer. Okay. So these numbers are not rational numbers. They are irrational numbers. So we have got on the number line a set of all rational and irrational numbers. And all these numbers exist. They have a place on the number line. Hence, all of these are all real numbers. Is it clear, children? Okay. Now, I have got one very interesting number for you. Root of minus 5. Does this root of minus 5 have a place on our number line? If it has a place, then it must be a real number. So, we should know the value of root of minus 5 for us to locate it. So, suppose I have got any number A. If I have to find the root of A, then I have to find a number B such that when I multiply B by B, I multiply the given any number by itself, I must get back my A. Isn't it, children? So, if I have to get back minus 5, I have to find two numbers so that the product has to be minus 5. And they have to be the same number, even with the sign. That is the meaning of same, identical. Okay. Now, if I take two positive numbers and multiply it, I will not get a negative number. It is positive. And if I take two negative numbers and I multiply it, I get again a positive. I don't get a negative one. So is it possible for us to get two identical numbers such that when you multiply it, you will get a minus sign? Not possible. Isn't it, children? So that means the value of root of minus 5 does not exist. It is imaginary. That means it is not real. Okay, children. So the real numbers consist of all the rational and irrational numbers that we have located on the number line. So this is the basic concept about real numbers. Is that clear, children? Let us proceed further for this year's lesson, wherein we are going to understand about application of real numbers. I have a situation here, children. In the sense, there is a merchant. He has got two kinds of oils. Okay. One of 120 liters and other of 180 liters. He wants to pack them all off in tins of equal volumes and then sell them. He doesn't want to sell in small amounts. He wants to just pack all of them in tins of equal volumes and just sell them off. Okay. So find the greatest volume of such a tin. So what can be the greatest volume so that he can sell all of them in equal quantity? That is the problem. Fine. What does that mean? He has to divide these 120 into a number of cans with certain volume, and 180 also he wants to pack them in the same can. He doesn't want to have for oil a different can of different volume, and for B he doesn't want. He wants to have cans of equal volumes for both the kinds of oil and pack them. That is the meaning of this. That means 120 has to be divided into equal amounts. 180 also has to be divided into the same equal amounts. So we have to divide them. That means we have to find a common divisor for both of them. Okay, so we have to find a common divisor for both 120 and 180. And what is this process of finding a common divisor known as? Yes, finding the HCF. We have to find the HCF of 120 and 180. I think this method of finding the HCF we have learnt in the very small classes. We will take up that method now. Okay, so 180 can be written as 10 into 18 and 120 can be written as 10 into 12. Okay, and what does this mean? 180 is equal to 10 into 18 means that 180 is divisible by 10 and 18. 180 is divisible by 10 and 180 is divisible by 18. That is the meaning. When we write 180 is equal to 10 into 18, it means that 180 is divisible by both 10 and 18. So also 120 is equal to 10 into 12 means 120 is divisible by both 10 and 12. So you can say that we have got a common divisor here, 10 liters. So he can have 10-liter cans or tins and fill them up. No, he is not satisfied, our merchant. Why? He wants the greatest volume of such a tin. That means he wants to make big cans. He doesn't want smaller ones. As big as possible with this, he wants to make. Okay, so we can further factorize this. 180 can be written as 60 into 3 and 120 can also be written as 60 into 2. So now we have a common factor, isn't it? 180 is divisible by 60 and 3. 120 is divisible by 60 and 2. Okay, children. So what is our HCF? HCF is 60. So our merchant can make cans of 60 liter each for both the oils. 120 liters he will make 2 cans and for 180 liters he will make 3 cans. All are 60 liter cans and he will sell them. Is it clear, children? Okay, fine. We have used this basic concept of finding HCF. Later on, when you went to a little higher classes, you would have learnt HCF by another method. What is that method, children? Yes, it is the division method. Okay, so let us go through this division method and see how we did it. Okay, we took the bigger number. Which is the bigger number of 180 and 120? 180, and we divided this 180 by 120. So we divided it, it goes once, 120, 60 is a remainder. Again we took this 120 and we divided 120 by 60. Okay, that is the divisor becomes the dividend and 60, the remainder becomes the remainder becomes a divisor now. Okay, and since the remainder is 0, the HCF is 60. So this is another method we have learnt in the lower classes. Now we will use this method to decipher yet another method. Okay, children, shall we go through that? Yeah, consider just this first part, 180 being divided by 120. Okay, children. So in our lower classes, we would have done one cross checking to see what whether our division is correct or not. What did we do? Yes, we know that this 180 is called as the dividend. Dividend is 180. 120 is the divisor. So 1 is the quotient and 60 is the remainder. To know whether our division is correct or not, we used one formula. What is that formula known as? Yes, dividend is equal to divisor into quotient plus remainder. We used to do this for cross checking. So let us again use that here now. Which is the dividend? 180. 180 is equal to divisor is 120 into quotient is 1 plus 60. We'll write that. 180 is equal to 120 into 1 plus 60. And we know that this remainder must always be less than. This remainder must always be less than the divisor. Can it be more than this divisor? No, it cannot. If it is more, that means that you can divide it further, isn't it? Suppose we had 121 as a remainder, say out after dividing, and we are dividing by 120. It means that we can divide it further. We cannot have a remainder bigger than the divisor. Isn't it? So here we have written that 60 is less than 120 we have written. And then what did we do? We divided it further. That is, this 60, the remainder became the divisor, and then this 120 became the dividend now. Okay, so 60, the remainder, became the divisor. That means we are going to divide by 60. Which number are we going to divide? The previous divisor. Okay, so the divisor becomes the dividend and the remainder becomes the divisor now. So we can write that 120 is equal to 60 into 2 plus 0, and we know that 0 is less than 60. The remainder 0 is less than 60, which is nothing but the divisor. Okay, since we have got the remainder as 0, our HCF is 60. Is it clear, children? So this is the other method that we can use it. So let us understand a little more about this by taking one more example. Say we have to divide 19 by 5. So 19 and 5 are the numbers that are given to you. Okay. Now using these numbers, which will be the dividend? 19. The bigger number will be the dividend and the other number will be the divisor. Okay. So using this format, dividend is equal to divisor into quotient plus remainder. How do we write this 19 when we want to divide 19 by 5? Yes, we can write it as 19 is equal to 5 into 3 plus 4, where 3 is the quotient. 3 is the quotient and 4 is the remainder. 3 is the quotient and 4 is the remainder. And we know that the remainder is between 0 and 5, where 5 is the divisor. Okay, children. So this is how we can write. And we are already given these two numbers, 19 and 5. That means we must use 19 equal to 5 into something only. Can we write this as 19 is equal to 5 into any other number? For example, can we write this as 19 is equal to 5 into 2 plus 9? No, we cannot, because in that case the remainder would have become 9 and this remainder would be greater than our divisor. What is our divisor? 5. 5 is our divisor. It cannot be greater than the divisor. 9 becomes greater than the divisor. Okay, the remainder. We must always have the remainder less than the divisor. This means that we can divide it further, isn't it? So we cannot write this as 5 into 4 plus 9. Can I write 5 into 2 plus 9? Can I write this as 5 into 4? 5 into 4 itself becomes 20, which is greater than our required number. So there are no other ways of writing except this way. This is the one and only way of writing this statement. 19, given 19 and 5, given these two numbers, we have got only one way of writing. So we say that this is a unique way. That means our quotient and remainder are unique. This 3 and 4 are unique when you are given these two numbers, 19 and 5. Suppose you are given something else, 19 and 6, then there is got only one way of writing. You would have written it as 19 is equal to 6 into 3, isn't it? 6 into 3 plus 1. Then, so given these two numbers, you have got, that is A and B. You are given the number A and another number B. Two numbers you are given. This quotient and remainder becomes unique. Is it clear, children? So, given two numbers, we have got a quotient and a remainder that is unique, and it can be written only in this manner. Let us take another example. Say we want to divide 26 by 6. Okay, 26 is the bigger number, so we can express 26 in terms of 6 as 26 is equal to 6 into 4 plus 2. And this remainder 2 lies between 0 and 6, where 6 is our divisor. Okay, children, our remainder 2 lies between 0 and 6, where 6 is our divisor. Okay, so we have got numbers which can be written in this format. 19 is equal to 5 into 3 plus 4, and 20 is equal to 6 into 4 plus 2. That means, given any two numbers, we were given 19 and 5 in the first case. In the second case, we were given two numbers, 26 and 6. That means, given any two numbers A and B, we can write it in the form A is equal to B into Q plus R. Here we had 19 and 5 was given, 5 into 3. 3 is a quotient and 4 is a remainder. 26 is equal to 6 into 4. 4 is a quotient and 2 is a remainder. So we can, given any two numbers A and B, it can be written in the form A is equal to B into some quotient plus R, where R is the remainder, and R can take all values between 0 and B, which is the divisor. So in general, given positive integers A and B, okay, both are positive integers, and one number will be greater than the other. We consider A is greater than B, then there exists unique integers Q and R. We have already seen that. Satisfying this relation, A is equal to B Q plus R, and where R will lie between 0 and our divisor B. It can also be equal to 0, our remainder. So we write it as 0 less than or equal to R less than B. This statement means that our remainder lies between 0 and B. It can be equal to 0 as well. Okay, children. So this statement has got a special name and is called as Euclid's division lemma. This was first compiled by Euclid, the great mathematician Euclid, and since it is used for division, it's called as Euclid's division lemma. Lemma simply means a statement that is already proven, and it can be used for proving other statements. So this statement that given two positive integers A and B, where A greater than B, there exists unique integers Q and R. For a particular pair of numbers A and B, Q and R will be unique, and it satisfies this equation A is equal to B Q plus R, where our R lies between 0 and our divisor. It can be equal to 0 as well. So this statement is called as Euclid's division lemma. Is this clear, children? Okay, let us understand this with an example. So let us use Euclid's division lemma or algorithm. Both are used. Both these words are used. They mean the same, to find the HCF of 135 and 225. So which is the bigger number here, children? 225. So we write 225 in terms of 135. So we can write 225 as 135 into 1 plus 90. Okay, children, 135, you can divide 225 by 135 only once, and we have the remainder 90 here. Okay, since we have a remainder, we should divide this further. So how do we do that? This 135 becomes the dividend now. 135 becomes the dividend, and our remainder 90 becomes the divisor. Is it clear? The divisor becomes the dividend and the remainder becomes the divisor. Okay. So now we can write 135 is equal to 90 into 1 plus 45. Again we have 45 as the remainder. So we can proceed with this revision again. Now what happens? 90 becomes our dividend and 45 becomes our divisor. Is it clear, children? 90 becomes our dividend and 45 becomes our divisor. So we have to express 90 in terms of 45. 90 is equal to 45 into 2 plus 0. Since we have the remainder as 0, our HCF will be the last divisor here too. Okay. So the HCF of the numbers 135 and 225 is 45. This is how we use Euclid's division lemma to find the HCF of any two given numbers. Let us do one more problem so that it becomes clear to you, children. 196 and 3822. Okay. So which is a bigger number? 3822. So we can write 3822 equal to 196 into 19 plus 98. Okay. You can either, actually you should not be dividing here. We should take this bigger number 3822 and divide it by 196. Okay. A small mental calculation will be required. Quick mental calculation, children. So here we have got 3 digits. That means we have to take the first 3 digits here. 382. Okay. So 196 twice. How much? If you want, you can do it 196 into 2. Or a quicker method is 196 is very close to 200. So we take twice 200, which is 400. And 196 is 4 short of 200. So 196 into 2 must be 4 into 2, 8 short of 400. So 400 minus 8 is 392, children. Isn't it? So 196 into 2 will be 392, but we have got only 382 here. So we cannot take it twice. Hence we have taken 1 here. Is it clear, children? We have taken 1. So 382 into 1 is 382. No, sorry, 196 into 1 is 196. And we know that if we are 10 short, we didn't have a 392, we had 382. That means for 196, it is 10 short. Isn't it? So the remainder will be 186. Did you get that point, children? This is how mentally you should calculate. So 186 is the remainder. With this next digit, we have 1862. Okay. 1862. 196 into 10 is 1960. Isn't it? So we have only 186. So we should try with 9. Okay. That we can just multiply and then find out the remainder. So sometimes such mental calculation is required. If you were to divide actually, then this Euclid's lemma will not be of any use. You will have to do it by the division method. So this mentally you will have to practice doing it. Okay, children. So 3822 is equal to 196 into 19 plus 98. Now what happens to 196? 196 becomes our dividend and 98 becomes our divisor. Is it clear, children? So we have to express 196 in terms of 98. So what do we get? 196 is equal to 98 into 2 plus 0. Now what is the remainder? Remainder is 0. So what is our HCF? The last divisor, that is 98. So the HCF of 196 and 3822 is 98. Is this clear, children? Please practice a few more problems from your textbook as well. Okay. And then this will become clear to you. Okay. Let us proceed further. What do the following mean? So whatever we have understood, let us fine tune it and try to understand the meaning of some mathematical statements. 63 is equal to 12 into 5 plus 3. So this is of the form A is equal to BQ plus R. Isn't it, children? This is of the form A is equal to BQ plus R. So this means that there are two numbers 63. That means 63 is B is 12. When 63 is divided by 12, the quotient is 5 and the remainder is 3. Okay, and we see that 3, the remainder is less than our divisor 12. 3 is less than 12. Okay, so that is the meaning of this. So when 63 is divided by 12, the quotient is 5 and the remainder is R. That is the meaning of this statement. Okay, let us see one more example. 455 is equal to 42 into 10 plus 35. Okay, so this means that when 455 is divided by 42, the quotient is 10 and the remainder is 35. That is the meaning of this statement. You must be careful. You cannot say that here this is our B and this is our Q and this is our R. Okay, please don't interchange to say this is B and this is Q. Okay, that means in that case what happens, our remainder will become greater than our divisor. B is the divisor. That should not happen. You must be careful to see that your remainder is always less than the divisor. So here our divisor is 42, quotient is 10 and remainder is R. This is the correct way of saying it. That is the meaning of the statement. You should understand what is the meaning of this statement when it is given. This will help you for your further problems, solving further problems. Okay, children? Okay. Now, one more. Suppose you are given in words how you write it in the mathematical statement form. For example, you are given that a number A divided by 2 gives quotient Q and leaves remainder 0. That means your number A is some A and your B is 2 here. You got it, children? Your A is A and your B is 2, Q is Q and remainder is 0. That means R is 0. So how do you write this in that mathematical statement using Euclid's division lemma? We write it as A is equal to 2Q plus 0. So given statement in the literal form, you must be able to write it in the mathematical form. Given a mathematical statement, you must be able to decipher the meaning in the literal form. These two are also important for you. Is it clear, children? Now, one more. A number B divided by 6 gives quotient Q and leaves a remainder 4. So our number is B. So B is equal to divided by 6. That means B is 6. Okay. Our B. What we call A is B and what we call B is 6. Okay. So B is equal to 6 into Q. Remainder R is 4. So we have B equal to 6Q plus 4. I hope all these concepts are clear, children. Please run through the video again and make all these clear before we get into the next session. Okay, and I have got some. Let us take a quick recap on what we have learned today. We have learned to find HCF using Euclid's lemma. We have learned how to convert statements into mathematical statement and understand the meaning of mathematical statements. These are the things that we have learned today. Very simple, children. We have just learned about Euclid's lemma. Whatever I have told so far is for you to understand the concept. That's all. Okay. So it is just Euclid's lemma that we have learned. That is A is equal to BQ plus R. And the remainder must always be less than the divisor. A concept that we already know it and we have learnt it in the lower class has been put into a different form. That's all. There is a saying, old wine in a different bottle. Something like that. Okay, children? Fine. And I have got some thing for you to do it on your own. I want you to do this. Please take these problems and do it on your own, and we will discuss these answers when we meet with the next video. And all of you, if you have any doubts, I hope you all have understood. If you have any doubts, please put them in the comment section. I will get back to you as soon as possible. Thank you for watching this video, and please don't forget to subscribe, like and share. Thank you once again.